This lecture is about singularities, different types of singularities that we find in complex functions. Singularity. Now, what is the singularity? Singularity is a point where a complex function is not analytic. It may be analytic in the neighborhood of that point, but right at that point, it is not analytic. And there can be various reasons for not being analytic at that point. Accordingly, singularities, they are of different types. For example, say suppose we have this just one type of singularity. Suppose you have f z is equal to 1 by z minus a, and at a, if z is equal to a, then the function is not defined. The function what we call blows up. If we draw a graph of this function and let this be a, then what happens that as z tends to a, this denominator decreases. A decreasing denominator creates a large number here, and so z, it is the graph goes like this. It goes something like this, and then when z goes that z increase above this, the graph comes back like this. Something like this happens near this point a. The function itself is not defined. Now, this is one type of singularity. At this singularity, what we see that the function is not defined. But there can be other reasons as well. As you will find, we go on defining these singularities, we go on classifying these singularities. You will find other singularities as well. Singularities in general can be classified into two groups. One is isolated singularities, and then there is isolated singularities. Isolated singularities, and then there is another group that is, just a minute. Isolated singularities, and then there are other types of singularities called non-isolated singularities. Non-isolated singularities. Okay, let us first clarify the difference between them. What this is. We, for that matter, we use two examples, one for this, one for this. Suppose I have a function fz which is equal to 1 by sine pi by z. Now I ask myself, why can this function have a singularity? Why is this function, for example, not defined? Of course, if this denominator is 0, often what we do is we start with the denominator, put it equal to 0, and that tells us that the function will not be defined at those points. Sine pi by z equal to 0. Now if sine pi by z is 0, it means that 1 by sine pi by z that is not defined. Okay, but sine pi by z means 0, means it is as if sine theta is equal to 0, and we know where sine theta is equal to 0. Sine theta is equal to 0 for theta equal to 0. Then it is again 0 for theta equal to 180 degree, that is pi. Then again 2 pi here. Then again 3 pi. That means it is 0 for pi, 2 pi, 3 pi, first 0, then pi 0, pi, 2 pi, 3 pi. In short, it is 0 for theta is equal to n pi, plus or minus theta equal to n pi. Let us take plus branch, that is n pi. That means pi by z. Since here theta is pi by z, so pi by z will be equal to n pi. Well, so if pi by z is equal to n pi, it means that pi, you can cancel pi, and then you get 1 by z. 1 by z is equal to n, which gives us z is equal to 1 by n. This means that at every value that is given by this, If z is equal to this, then this will be 0 and the function will not be defined. That is, there are singularities at these values. But what is n? N is an integer, and n is equal to integer x. We will not take n equal to 0. Let's take n equal to, say, for example, 1. When you take n equal to 1, here's a, let us show this real line. Here is 0, and let us approach this point along the real line. So when we approach along the real line, suppose when n is equal to 1, z is equal to 1, that is here, this is 1. Give n value 2, z will be equal to 1 by 2. There will be a singularity here, there will be a singularity here, because this corresponds to n equal to 1, this corresponds to n equal to 2. Then take n equal to 3, this point, this will be another singularity here. N equal to 4, another singularity here. N equal to 5, that is 1 by 5, another singularity here. N equal to 6, another singularity here. What do we observe? We observe that there will be singularities at n equal to, say, n equal to 1, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, and so on. But see, these singularities, as n increases, these singularities, they approach each other. They come closer and closer, closer and closer, closer and closer. And when we approach 0, this 0, as we approach this 0, these singularities will accumulate there in such a way that there will be no region, however small, around 0 that will be left without a singularity. That means 0 will be surrounded by singularities from all sides in a small neighborhood. If you take this neighborhood of 0, very, very small, very, very small, in that very, very small neighborhood, this 0 will be surrounded by these singularities. When a point is surrounded by singularities from all sides in such a way that no region is left, no region around that point is left, however small that region may be, but no such region is left around that point without singularities. It is something we can say that the region around this point is dotted with singularities. Every point is a singularity. So you cannot have any convergence disk here. Now, there is no possibility of an expansion of a function around such a point. This point is called this is called non-isolated singularity. This point, it is not isolated. It is not isolated. It is surrounded by other singularities. Now, if you have a non-isolated singularity, you can neither apply Lorentz for this series expansion nor Taylor series expansion. Let us go to now isolated singularities. Isolated singularities. This was an example of non-isolated singularity. Now, isolated singularities. Let me take this fz. Fz is equal to fz. I will clean some space here so that I am able to utilize that for this 1 by sine z. Now the situation, see, this fz will have singularities at all points where sine z is equal to 0. Well, sine z is equal to 0. Okay, that means z is equal to n pi. That means z is equal to pi, then 2 pi, then 3 pi, then 4 pi. Let's show these singularities along this x line. For example, here 0, this is 0. Now pi, there will be singularity here, 2 pi singularity here, 3 pi singularity here, 4 pi singularity here. There is no singularity here which does not have a region around it which is without singularities. Look at this, around this 2 pi, this region that I have shown by a circle, this is a region where there is no singularity except at 2 pi. So this singularity is surrounded by a region where there is no singularity. This singularity is surrounded by a region where there is no singularity. This singularity is surrounded by... So singularities do not crowd up here as they did here. So these singularities are called isolated singularities. They allow us to expand these functions whether in Lorentz series or in Taylor series. It is these singularities. So series expansion, for series expansion, we must have isolated singularities. Proceeding ahead now, proceeding on, we have now isolated singularities, several types of them. Isolated singularities. We have several types of them. Isolated singularities. Isolated singularities. Three types of them. One is removable singularity, or it is better. No, it is okay. It is okay. Removable singularity. Then there is another type of singularity known as pole. Then another type of singularity that is called this essential singularity. Essential singularity. Now let us see what these are. All of them removable, pole, or essential singularities. All of them are isolated singularities. Let's take first removable singularity. This removable singularity is a singularity such that the function, of course, is not analytic at, say, suppose there is a removable singularity as z equals to a. The function is not analytic at a. However, if we take limit of the function as z tends to a, limit fz that exists and has a finite value that exists there. Although the value of the function, that is fa, does not exist, but limit of the function as z tends to fz that exists. Let me show with an example. Now this is called removable singularity because this singularity can be, as its name tells, it can be removed easily by redefining the function. For example, let's take the case of fz is equal to sine z by z. Now function z equal to 0. Put z equal to 0. This is 0 divided by 0, not defined, indeterminate. Here is a case that is different from not defined or undefined. It is 0 by 0 when z is equal to 0. When z is equal to 0, it is 0 by 0. So anyhow, it is not, it is indeterminate, hence not analytic at this place now. However, see, look at the limit. If z tends to 0, fz will be equal to limit sine z by z, z tends to 0. And see, this is the famous limit, sine theta by theta, and everyone knows it is 1. So limit of the function does exist, although the function does not exist. This is the characteristic of a removable function. This removable singularity. Now, why we call it removable? We shall see that at proper time as we go in this video. Actually, in this video, we will see how we can do it. Now, how it's removable. Okay, let us go to pole. Pole is another singularity, another type of singularity. At pole, what happens? If there is a pole at z is equal to a, then limit z tends to a, fz is infinity, that goes to infinity. It is infinity. This is finite, not infinity. Finite here, just as you saw it here. This is infinity, it goes to infinity. As an example, suppose let us take an example, this function. We have say fz is equal to 1 by z minus I. As z tends to I, fz will tend to infinity. This is pole. We say that z is equal to 1 is pole, right? Here at pole, you see the denominator blows up. So this is the pole, at which limit of the function goes to infinity. Okay. Now this is we will study more about these things. And poles have order. Suppose you have a pole fz is equal to 1 by z minus I squared. This again, z is equal to I is pole, but now it is called, it is said to be pole of order 2. This is said to be pole of order 1. Then similarly, you can think of pole of order m. Now, essential singularity. Essential singularity. Say, essential singularity. This essential, so yes, one more thing that I needed to tell you is that when we use Lorentz series expansion for a function, in the singularity that we call removable singularity. In case of removable singularity, Lorentz series expansion does not have any negative power. You know that Lorentz series expansion is this: fz is equal to, it has two parts. One is for these positive powers, another for negative powers. N is equal to 0 to infinity Cn z minus a raised to n. Then another is plus n equal to 0 to n equal to 1 to infinity Cn z minus a raised to minus n. Okay, or we can write it minus Cn, C minus n. Now these are this part of the series consists of powers which are negative powers of z minus a. The expansion involves negative powers of z minus a. In Taylor series, we have only positive powers. This part of the functions, a Lorentz series, is in fact called principal part of Lorentz series. Now, if in removable singularities, if a function has removable singularity, then it does not have any negative power of this Lorentz series. No negative power in Lorentz series expansion of the function. Now, in case of poles, if there are poles in the function, then there are negative powers, but negative powers are finite in number. That means you can have, for example, just as I showed you, fz is equal to 1 by z minus I is a negative power, that is 1 minus 1. You can bring it up and write z minus 1 minus 1. Similarly, you can have, say, fz is equal to 1 by z minus I raised to, say, cube. The negative power is minus 3. So these are Lorentz expansions where powers are negative. In case of pole, you have negative powers in Lorentz series expansion. Then the third is this essential. This singularity, essential singularity. Consider, for example, let's take as an example, in order to understand it, let's take this e raised to minus 1 by z square. Let's expand it as if we treated this whole as if this is 1 by z. This is e raised to, treat it as if it is e raised to z, and you know e raised to z is 1 plus z square by 2 factorial plus z cube by 3 factorial and so on, plus dash dash. Now treat this as if you have this z square and expand it like this. It will be, you will get 1 minus z, in place of z we have this 1 by z square plus 1 by 2 factorial 2 I will write like this, otherwise it looks like z 2 factorial z4 plus dot you have z4, but z4 in the denominator, sorry, it is 1 by, so it will be this will be here 1 by z4. Similarly, there will be a next term z6, then so on. There will be no end to it, up to infinity. Okay, now you have this. Now this is Lorentz series expansion, because again you have negative powers. You can see negative powers. Now, if the number of terms, it is not the case of one pole, for example, z equals 0, that will blow this up. But it's not the case of one pole here. There are poles and poles and poles up to infinite number of such negative terms. We call this we would call it z equal to 0 a pole had there been only a finite number of terms that contain these negative powers. But when the number of terms is infinity, we call them essential singularity. And characteristic of essential singularity, let's watch. Let's have a little bit discussion on this. See, I have expanded this like this. Oh, and see, if I now do one more thing, that is, if I can say, suppose this is complex plane. Let me approach this function. Let me approach z equal to 0. Z equal to 0. Let me approach z equal to 0 along the real axis, either from right or from left. They will yield the same answer. If I approach z equal to 0 from real axis, then at that time I can consider this e raised to if z tends to 0, z approach 0 along real axis, then I can replace this e raised to minus 1 by z square equal to e raised to minus 1 by x square. X, because y along this is 0. Now, and in that case, this expansion, now see what will happen. As x tends to 0, imagine this x tending to 0. Say from right, it is tending to, it doesn't matter whether it tends to 0 from right or left, because it has a square. This square will neutralize negativity of the numbers. So it will be x, as x tends to 0 from right. Now x decrease in now it is magnitude. As the value of x decreases, 1 by x square will increase. It will go to infinity. As x tends to 0, it will go to infinity. And in that case, what will happen? E raised to, that is e raised to minus infinity, that that tends to 0. This means that it is limit. This will be z tends to 0, e raised to minus 1 by z square. I will write it here. E raised to minus 1 by z square is equal to 0. Now let's approach this function from this imaginary axis. As you approach it, if z tends to 0 now along imaginary axis, then you have now e raised to minus 1 by z square equal to e raised to minus 1 by iy square, because x is now 0. And in the this complex number is x plus iy. Previously we had y0, now we have x0, so it is this. So we have e raised to I square, that is minus 1, I square minus 1, so it will be minus 1, and in this minus it will be plus 1 by y square. And what happens now? As y tends to 0, this tends to infinity. E raised to infinity, that is infinity. Therefore, you see that if z equal to 0, we reach this conclusion. If z equal to 0, e raised to minus 1 by z square tends to infinity. Now, it means that the function limit is unstable. If you go via this, you find the function tending to infinity. And if you go like this, it tends to infinity. Sorry, in first case it was 0. In second case it is infinity. And who knows, in this case and this case, what will be the value of the limit. Now, this behavior is called unstable behavior or oscillation, which say the function this oscillates wildly from, say, why wild word? Because it goes from one extreme to another extreme. It is an extremist type of a function. Such a singularity is called essential singularity. Now let us proceed ahead. We have now we have discussed these. Just 1 minute. This is as we have completed them now. So we will now go for this some examples, some problems based on this I mean singularity. Let us go for them. Yes, one more thing, that is zeros of a function. Now, zeros are those values of z which make numerator 0. Zeros, as we have you must have studied about zeros of polynomials. It is almost the same thing. Zeros, for example, you have, let us take a function fz is equal to 1, say z minus 1 raised to 2 into z plus I, for example. Now you know this function can be, its value can be made to 0 if you put z equal to 1, z equal to minus 1. We say that this z equal to 1 and z equal to 1 minus 1 is a 0 of this. A 0 means a value of z which makes the function, value of the function, tend to 0. So this is 0 of second order, this is 0 of first order. Anyhow, now there is a relation that you expect between zeros and these poles. For example, suppose you have an fz which is a rational function, pz divided by you have qz, say something like this. For example, as an example, 3z square minus 2z plus 1 divided by say z square plus 1 whole square, for example. Now in this is numerator, this is denominator. Now suppose this has a 0 of order, say 0 of order p, for example, let's take p, small p, and this is 0 of order q, 0 of order q. Then if the order of the zeros is same here and here, same, then fz will not have any pole at all. If it is same, no pole, because 0 of that will cancel 0 of this, and the function will be left without any 0 at that, without any pole. Now however, if order of, say suppose order of q is more than order of p and difference between them is n, q minus p, then this function will have a pole of order n. So the function will be of course function will not be, it will not be analytic at that at those points, at that point rather. On the other hand, if p is greater than q, p, this number of zeros here, order of zeros here is greater than this, then the sum of them will cancel out these zeros of this, and the function whatever is left is analytic. It won't have any poles at all. Now let us go now to this problems based on this. Let us take, for example, first find singularity of question. Let us take question number 1 as find singularity of sine 1 by z. Quite simple. What you have to do, you have to simply expand this in Taylor series or this Lorentz series. You have to expand this using as we did the expansion of sine x. I don't remember it correctly, but I remember one thing, that it is let's try. I know one thing about sine, it has odd terms only, so let me use that knowledge, that memory, and see odd term. Now normally first term is 1, then this is, it has not odd terms, even terms. It doesn't have first term, perhaps. Yeah, it doesn't have first term, so 1 is not there. You see, this is Taylor series, fa plus f first term fa, then f dash a divided by 2 factorial plus f double dash a divided by 3 factorial, and so on. It has only odd. This sign, I remember, has odd, these odd. That means this term will be there, this term will be there, and then again that fifth will be there. That means divided by 1 will be there, divided by 2 will not there, divided by 3. So it is something like this. X first will be x, next will be this x cube, x by divided by this is the x, this x divided by 1. X, had it been square, then first term would have been this x square. Now x minus, then alternatively positive and negative, minus this, this is x square divided by 3 factorial plus x5 divided by 5 factorial plus. Now you might be wondering, how did sir know this x square, x cube? We are expanding it about x. Expanding it about x means the terms will have this, except for the first term. First term will not have x, then all the terms will have x, because you are expanding about x. So the power of the x will go on increasing. Okay. And the coefficients do not leave anything in the denominator, in the numerator. They leave everything in the numerator, in this denominator, that is 3 factorial, 5 factorial, and so on. Now, and one more thing, that is for sine and cos. This is an interesting thing, that sine and cos, all the derivatives either have value 0 or 1, because when you put x equal to 0, sine x is 0 and cos is 1. Now this is the, and using this, let us use this sine 1 by z is equal to 1 by z minus 1 by 3 factorial into 1 by z square plus 1 by 5 factorial into 1 by z 5 square cube. No, then it is x, then x cube, sorry dear, x cube, then x5 is, this is x cube there, x cube z raised to this x cube, that is 1 by z cube, and then 1 by z5, and so on. Looking at this, you can see yourself, there is no end to these negative powers. Negative power here is -1, negative power here is -3, negative power here is -5. So Lorentz series expansion has only negative powers, and there's no end of the negative powers. It has negative power, but no end. They are infinite in number, and hence this singularity, such a singularity is called essential singularity. This, so z equal to 0 is an case of essential singularity. Let us now go for z equal to this singularity of this. For example, let's find singularity of e raised to 1 by z divided by z square. Now quite easy. Once again, what you have to do is 1 by z square, you have to keep it as such, and then expand this e raised to 1 by z, that is 1 plus 1 by z plus 1 by z square. This is expansion of this 1 by z square plus dash dash dash, something like this. And then when you multiply this with this, you get 1 by z square, 1 by z square plus 1 by 2z square plus 1 by z4, 1 by, sorry, it is not 2z square, it is z cube plus there is one more thing that I forgot, it is 1 by 2 factorial z square, 2 factorial z square. Anyhow, my point is that this again is a non-ending negative power Lorentz series expansion. Hence the given function has z equal to 0 as it is essential singularity. Next, find poles of this. For example, say e raised to z minus a divided by z minus a square. Okay. In order to find poles, we will have to first expand this. As usual, we have 1 by z minus a squared, and then 1 minus, now it's expansion, that is z minus a plus this, something like this. You can work it out yourself. So here you have z minus a, then you have z minus a squared, then z minus a cube. Those are powers, positive powers. That means they are in the numerator. They will not create poles, and poles are all due to this z minus a square. And we have z equal to a is a pole of second order. Now, having done these few problems, we can add a few more. Say we can go for this, we have suppose for example we have fz is equal to sine 1 by z minus a, and what we have to do, we have to again find its singularities, and at, say, you can see yourself at z equal to a, it has a singularity at z equal to a. Now what type it is, you will do that by expanding this in Taylor series. It is again quite simple. Now again it will be essential. Then we have another something like this. Say for example you have cot pi z divided by this cot pi z divided by z minus a squared at, say, z equal to a, for example z equal to a. Now you can write this as cos pi z divided by sine pi z, because it dealing in terms of sine and cos is much easier than cot. Now we are familiar with these. Now zeros will be this denominator will be this poles will be sine pi z, rather singularities will be sine pi z into z minus a squared. And what you have to do, you have to you then that will be equal to 0. Now that this means that if sine pi by z is equal to 0, then singularities will be at this pi z is equal to n pi. Pi goes, z is equal to pi. So and z is equal to pi. No, pi goes, z is equal to n. That is, singularity will be at 1, 2, 3, 0, 1, 2, 3, 4 at these values. Now similarly you can you can, from this you get singularities at z equal to a. This is a pole of these are isolated, these singularities isolated, and z minus a square is a pole with of order 2. Now next, find the poles of, for example we have, say, let us say find poles of this fz is equal to 1 by 1 plus z4, 1 plus z4. Now you have 1 plus z4 is equal to 0, implies z4 is equal to minus 1, implies z is equal to minus 1 raised to 1 by 4. Now minus 1 can be written as cos n pi. Cos yes, of course, n pi, or let me write pi 1 n pi, for example n pi. Let me check n pi, that means cos is minus 1 at pi, this at pi it is minus 1. Then again it is not pi here, it is again pi here, it is not pi here. This means that not all, I cannot write n pi, because n, if n is 0, this will mean cos 0, and cos 0 is not equal to minus 1. If n is equal to 1, this will mean cos pi. Cos pi is really minus 1, that is minus 1. But if I write this n equal to 2, then cos pi is equal to 2 pi. Cos 2 pi is again 0. This means only at odd numbers. This one minus 1 is minus 1 at odd numbers. Now 3, that again will be minus 1. So I have to write it as say cos, I will write it as cos, I write cos 2n pi plus 1, 2n pi plus 1 cos 2n plus 1 pi, that is it. Now this is minus 1. Now I can add one more thing. It has raised power 1 by 4. I can add one more thing to it, that is, I can write 2n plus 1 pi plus I sine 2n plus 1 pi whole raised to 1 by 4 this will not matter, because this will not matter the last, because for the simple reason that sine 2n plus 1 pi is 0. Sine pi is 0, so it is any odd or in this even multiple, there will be 0. But what is the fun of this? Fun of this is that it becomes Euler's formula. Now you have cos, you see, it becomes cos theta plus I sine theta. Now, but here is a difference, that is, this cos theta plus I sine theta has power n. Now n, where I call this 1/4n, it has power n. Now there is a theorem called De Moivre's theorem. According to De Moivre's theorem, this will be then equal to this. This is equal to cos 2n plus 1 pi into that power divided by 4 plus I sine 2n plus 1 pi into that power, that is divided by 4. So I have here, this is my value of z. Now if I take z equal to 0, now you see all these values will create a pole here. Now they will create a pole here. Now you can see how many of them are there. N is equal to 1, n is equal to 1, n is equal to 0 first, n equal to 0. The pole will be at that time, pole will be, if you put n equal to 0 here, pole will be at cos 0 plus 1, that pi by 4, cos pi by 4 plus I sine pi by 4. You know the values of pi by 4 and pi by 4. Similarly, n equal to 1, similarly n equal to 2, similar n equal to 3, etc. All these. Now, the last example is fz is equal to 1 by z square into 1 minus z. Now we have this, say for example, this is our function. We have here two choices. We want to examine what is at z equal to 0. That means, of course, there is a singularity, but what type of singularity? In my this question, I have infinites, these singularities. I cannot call them poles because they are infinite in number. Well, as poles are finite in number, they are these are essential singularities, better essential singularity, because there are infinite number of them. Now let me go back to this. In this case, I have this. Once again, I want to see what at z equal to 0 I have. Z equal to 0, at z equal to 0, there is a singularity. No doubt about this, because you can put 0 here and you will get this. There is one more singularity that this function has, that is at z equal to 1. It is this. 1 is at z equal to 0, and there is at z equal to 1. Z equal to 1. Now z equal to 1. Okay. Now if I expand this function like this, fz is equal to, I can expand it like this, 1 by z square, and treat this geometrical, this expansion of this, that is 1 plus z square plus z cube plus dash dash. But provided z is greater than 0 but less than 1. That is the condition. That is the condition. This means that this series expansion is valid in this region, not beyond this, in this region. Okay. Another is, I can do one more thing, that is, I can expand the same function as outside this region. For example, for that matter, I can do one thing, that is, I can say I have this z square, 1 by z square into 1 minus z. Now this time I need this z to be greater than 1. mod z to be greater than 1. This means that 1 by mod z to be less than 1. Sorry, greater, this is greater than 1, 1 by mod z less than 1. Now, for that matter, I can do this thing, I can expand it like this. I can write 1 by z square into I can take z common from this, z common, I get 1 minus 1 by z minus 1 minus 1 1 by z minus 1. Now I will take this as minus 1 by z cube and set this right as 1 minus 1 by z 1 by z. Now since in this region, uh, 1 by z is less than 1, 1 by z is less than 1, I can expand it now by this Taylor's or this Lorentz series or using geometric series expansion formula, that is 1 minus 1 plus 1 by z plus 1 by z square 1 by z cube 1 by z cube, etc. Now to clean up some space here, I have then two expansions of the same function. One is this and in this region, and another is this. Fz is equal to, let me multiply this by z cube, it will be minus 1 by z cube minus 1 by z cube minus 1 by z4 minus 1 by z5 1 by z5 minus, and so on. But this is valid in this region, z greater than 1 less than infinity. Now my question is, what is at z equal to 0? What is at z equal to 0? According to this, at z equal to 0, there is a pole of this 0 order, the second order pole here, according to this. And what about this at z equal to 0? An essential singularity, because it's not going to end anywhere. So what is the correct answer? The correct answer is this: z equal to 0 is a pole of order 2. The question why? Answer is that this expansion is not valid at z equal to 0, not in here. This expansion is valid here in this region, so it has no right to classify this point, whereas this point is around, this expansion is around z equal to 0 itself. So this will uphold. This is valid. Z is equal to 0 is a pole of order 2. So my dear students, hope that you understand what poles are, what these other singularities are. We have now removable singularity. Why the word removable is there? We will go to residue theorem now, last topic of our this complex analysis, residue theorem. And in residue theorem, we shall study what this we shall discover what removable is. We shall actually use that property of these singularities, removable singularities. Okay, thank you.